Welcome to Center of Math's basic series on real analysis. Today we're going to talk a little bit about Riemann integration. So first, we want to define a partition. So we have some closed interval AB. Our partition is just a sequence of numbers where A equals x naught, B equals xn, and it's x naught, x1, x2, etc. Such that xi is strictly less than xi plus 1. So it's just some sequence of numbers that are spread out over this closed interval, AB. The width will just be the maximum distance between any two adjacent numbers in the sequence. So max absolute value of xi minus xi minus 1 for I between 0 and n. And so we say a function is a Riemann integral if this sum, if we have some, let's say f of x is defined on some interval ab, we take some partition of xi's on this interval, and so the sum I from I equals 1 to n of f of xi prime times x of I minus xi minus 1. X of I prime is just some number between x of I and xi minus 1. It's arbitrary. And we say as the width of this partition goes to 0, this sum will approach some number a, which will be the value of its integral. So more rigorously, as we say, as the width of the partition less than delta, this minus some number, absolute value of that is less than epsilon. So this approaches some value, which will be the integral of f of xi on the interval ab. So we can prove that the integral on the interval ab of f of x plus g of x dx for two Riemann integral functions, f of x and g of x, equals integral from a to b of f of x dx plus integral from a to b of g of x dx. So to do this, first we're going to choose two partitions and Riemann sums for f and g respectively. So we're going to have widths delta 1, delta 2, such that for x minus x naught less than delta 1 and delta 2, the sum S1 for some width, some partition with width less delta 1, S1 minus integral AB f of x dx is going to be less than e over 2. And we know this because f of x is Riemann integral, so it has, for some Riemann sum referring to a partition less than delta 1, this will be less than e over 2 for e, any real number greater than 0. We do the same thing for g of x. And so now we want to show for our sum, our function is f of x plus g of x. Xi is just any x between xi and xi minus 1. So we want to show for partition small enough, this gets as close as we want to integral a to b of f of x plus integral a to b of g of x. So we want to show this gets as close as we want to the thing on the right side. And so we're picking our partition to be of width less than the minimum of delta 1, delta 2, so both our inequalities apply. And so we're going to rearrange this and use the triangle inequality to get a Riemann sum of width less than delta 1. That minus integral from a to b of f of x dx. So we know this is going to be less than e over 2 because the width is less than delta 1, so this will apply. And the same thing for here, except with g of x, we're going to again have something less than e over 2. And so this plus that is less than e over 2 plus e over 2, which equals e. And so that tells us our Riemann sums of f of x plus g of x get as close as we want to these two values summed together on the right. And so we have this equality. So we can show the integral from a to b of c times some function f of x dx is equal to c times the integral from a to b of f of x dx, where f of x is some Riemann integrable function. So we're going to take some Riemann sum s of f of x, taking the width of the partition to be less than delta, so s minus integral from a to b f of x dx is less than e over the absolute value of c. So if we take our partition to be of width less than delta, then we have sum from I equals 1 to n, c f of xi prime again is just some value between xi and xi minus 1. That times xi minus 1 minus c times the integral of a to b of f. So the absolute value of that, we're going to pull out c to get absolute value of c times absolute value of another Riemann sum minus integral of a to b f of x. But this is just our ordinary Riemann sum difference for f of x. But since the partition is less than delta, so that this difference will be less than e over c, e over absolute value c. So this is strictly less than absolute value c times e over absolute value c, which is equal to e, and e being some arbitrary real number greater than 0. And so we see this Riemann sum will get as close as we want to this thing on the right side, and so we see these two have to be equal. Thanks for watching. Please check out centermath.org, check out our blog, and follow us on Facebook and Twitter. If you like these videos, please check out our other real analysis videos.